Ever wonder how things like really take off?
Hmm.
Not just a little boost, but like zoom growth,
Yeah.
like going viral online,
Right. Or
or maybe a runaway science experiment.
yeah.
That, my friend, is the power of the exponential function.
Absolutely.
It's not just bigger numbers.
Right.
It's a whole different way things can change.
Yeah.
So today,
Okay.
we are on a mission to demystify these functions.
Okay.
We've got this super cool audio lecture translated from Korean that's going to break it all down.
And you'd be surprised. You know how often exponential functions,
Yeah.
they pop up in the most unexpected places.
Okay.
It's not just some abstract math concept. It's
Right.
like it's the secret sauce
Okay.
behind, how your money grows in the bank,
Right, yeah.
how populations
That's
boom,
interesting.
even how we date ancient artifacts.
Okay, that sounds way more interesting than how I remember exponential functions from school.
Right.
I always got stuck on that whole a to the power of x thing.
Yeah.
What is the deal with that?
It seems simple on the surface, right?
Yeah.
But there's more to it than just repeated multiplication.
Okay.
Think of it this way.
Okay.
Imagine you're watching a colony of bacteria under a microscope.
Okay.
At first, there are only a few, and they divide slowly.
Right.
But then, as they multiply, there are more bacteria to divide.
Okay.
And the process, it speeds up.
Okay.
Suddenly, you're witnessing a population explosion.
Oh, I see. So it's not just that the bacteria are multiplying,
No.
it's that the rate of multiplication is increasing.
Exactly.
Because there are more of them around to multiply.
That's the essence of exponential growth.
Okay.
The more you have, the faster it grows.
Okay.
And to really understand this kind of growth,
Yeah.
we need to introduce a new character to the story,
Okay.
the natural logarithm, or LN for short.
See, logarithms always seemed a bit like magic to me.
Right.
Can you walk me through it like you're explaining it to someone who barely passed high school math?
Absolutely.
Okay.
Think of the natural logarithm as a kind of detective.
Okay.
It helps us uncover the hidden exponent that drives that exponential growth.
Okay.
Let's say we have the number 10,
Okay.
and we want to know what power we need to raise a special number
Yeah.
called Euler's number, represented by the letter E,
Okay.
to get 10.
Okay.
That's where ln comes in.
Okay.
The natural log of 10, written ln 10, gives us that missing exponent.
Okay, so E is like the secret code and the natural logarithm helps us crack it.
Precisely.
Okay.
And just like every good detective duo,
Right.
E and ln have a special connection.
Okay.
They're inverses of each other.
What does that mean?
It means they undo each other's actions,
Okay.
like a perfect mathematical dance.
I'm intrigued.
Yeah.
Tell me more about this E's character.
Okay.
It sounds like it holds a pretty important key to understanding all this.
It absolutely does.
Okay.
Euler's number.
Okay.
It's like the VIP of exponential functions.
Yep.
It pops up naturally
Okay.
in situations where things grow continuously,
Oh, okay.
like the bacteria in our example,
Right.
or the way money compounds interest.
Okay. This is starting to make more sense.
Okay.
So we've got exponential functions describing how fast things grow,
Right.
the natural logarithm helping us understand those growth rates,
Exactly.
and Euler's number, he's playing a key role in it all.
Yes.
But where do we go from here?
Now that we've set the stage,
Right.
it's time to dive into the fascinating properties of these functions
Okay.
and explore how those properties
Yeah.
translate into real-world applications that might surprise you.
All right. Lead the way. I'm ready to see these exponential functions in action. So we've got these exponential functions,
Right.
and we know they describe like crazy fast growth.
Yeah.
But what are some of their like
Okay.
superpowers, their special properties? I'm ready to see what makes them tick.
Well, one of the most mind-blowing properties is what happens when we look at the derivative of e to the x.
Okay.
Okay.
Back up a second. Derivatives,
Right.
those were always a bit of a brain twister for me.
Yeah.
Can you give me the plain English version?
You got it.
Okay.
Imagine you're on a road trip
Okay.
and you want to know your speed
Right.
at any given moment.
Right.
The derivative tells you exactly that.
Okay.
It's the rate of change
Right.
at that specific point.
Okay. So if we're talking about the derivative of e to the x,
Yes.
we're talking about how fast it's growing
Yes.
at any particular point.
You got it. And here's the kicker.
Okay.
The derivative of e to the x is,
Okay.
drumroll please,
Okay.
e to the x.
Whoa, hold on.
Right.
It's its own derivative.
It is.
That's like saying a car's speed is always the same as its location,
Right.
which obviously doesn't make sense in the real world.
It seems counterintuitive,
Yeah.
but that's the beauty of e.
Okay.
It's the only function that grows at a rate exactly equal to its current value.
Hmm.
That's why it pops up in so many natural phenomena.
Yeah.
It's It's like the mathematical equivalent of a self-sustaining chain reaction.
Okay, that is mind-blowing.
Yeah.
So his isn't just some random number that mathematicians like to throw around.
Right.
It has this incredible property that
Yeah.
seems almost magical.
Precisely. It's like the mathematical embodiment
Wow.
of natural, uninhibited growth.
Okay.
And this unique property
Yeah.
leads to other fascinating characteristics
Okay.
of exponential functions,
Okay.
especially when it comes to those exponent rules
Right.
you might remember from algebra.
Oh, you mean like when you multiply exponents with the same
Yeah.
base,
Yeah.
you add the powers?
Right.
To be honest with you, I always just memorized the rules. I
Right.
never really understood why they worked.
And that's where the connection to logarithms makes everything click.
Okay.
Let's take an example.
Okay.
2 to the power of 3 times 2 to the power of 2.
Okay.
Remember, taking the logarithm is like asking, what power do I need to raise the base to get this number?
Right. So for 2 to the power of 3, the logarithm would be 3. And
Right.
for 2 to the power of 2, it would be 2.
Exactly. Now, when we multiply these exponential terms,
right.
we're essentially adding those hidden exponents.
Okay.
That's why 2 to the power of 3 times 2 to the power of 2
Right.
is the same as 2 to the power of 5.
Okay. I think I'm starting to see the light here.
Okay.
So by understanding logarithms,
Right.
those exponent rules aren't just some arbitrary operations anymore.
Right.
They reflect a deeper relationship.
Exactly. It's like we've unlocked the secret level
Yes.
of understanding.
That's right.
And this deeper understanding
Yeah.
helps us appreciate the true power
Okay.
and elegance of exponential functions
Right.
in describing the world around us.
Okay, I'm hooked. You mentioned some real-world applications earlier.
Right.
Can we dive into those now?
Oh, yeah.
Give me an example where all this mind-blowing math becomes something I can actually wrap my head around. All right, hit me with a real-world scenario
Okay.
where all this exponential action comes into play.
Okay, let's talk money.
Okay.
Ever heard the phrase,
Yeah.
compound interest is your friend?
Yeah.
That's exponential growth at work.
Oh, yeah, it's like that saying,
Right.
the more you have, the more you get.
Right.
But in this case, it's more like
Yes.
the longer it sits, the faster it grows.
Exactly.
Okay.
Imagine you invest $1,000
Okay.
with a 5% annual interest rate
Okay.
compounded annually.
Okay.
In the first year, you earn $50.
Right.
But here's where it gets interesting.
Okay.
In the second year, you earn interest not just on your original $1,000,
Right.
but also on that $50 you gained,
Oh.
for a total of $1,050 earning interest.
Okay.
Each year, the amount you earn grows
Right.
because you're earning interest on your interest.
Right.
That's the power of the exponential function.
So it's like a snowball effect,
Okay.
but with money growing exponentially.
Precisely.
Yeah.
And this concept applies to way more than just
Right.
personal finance.
Okay.
Think about population growth.
Okay.
Under ideal conditions, a population can grow exponentially
Right.
because each generation contributes to the next.
Right. So more people means more babies,
Right.
which means even more people
Yes.
in the next generation.
Exactly.
It's that bacteria colony under the microscope all over again.
You got it.
Okay.
And on the flip side, we have things like radioactive decay.
Okay.
The amount of a radioactive substance
Okay.
decreases exponentially over time.
Okay.
It's like a clock that runs backward.
Wait, so how does that work?
Every radioactive substance has something called a half-life,
Okay.
which is the time it takes
Right.
for half of the substance to decay.
Okay.
Let's say we start with 1,000 grams
Okay.
of a substance with a half-life of 100 years.
Okay.
After 100 years, we'll have 500 grams left.
Right.
After another 100 years,
Okay.
we'll have 250 grams,
Okay.
and so on. See the pattern?
Yeah, it keeps halving over time.
Right.
Which is, wait a minute, that's
Yeah.
an exponential decrease.
Exactly.
Okay.
And scientists can use this predictable decay to their advantage.
Yeah.
For example, with carbon dating.
Right.
They measure the remaining amount
Okay.
of a specific radioactive carbon isotope
Okay.
in ancient artifacts
Right.
to determine their age.
Wow. So we've gone from like to the power of X
Right.
to unlocking the secrets of natural logarithms and Euler's number,
Yeah.
all the way to understanding things like compound interest and carbon dating.
It's all connected.
Who knew exponential functions could be so fascinating?
Right. It's amazing, isn't it?
This deep dive has definitely changed the way I think about exponential functions. I'm
Sure.
seeing them everywhere now.
That's what we like to hear. And, you know, speaking of seeing things,
Yeah.
remember those graphs we talked about earlier? Like
Yeah.
7 to the x,
Yeah.
2 to the x, and 8 to the x.
Right.
Now that we've seen these functions in action,
Yeah.
maybe you can picture how those graphs would look.
Right.
What makes each one unique?
Yeah.
Think about their growth rates,
Yeah.
their connections to logarithms,
Right.
and all the amazing applications that we've discussed today.
It's really incredible how much depth there is to this
Oh, absolutely.
seemingly simple
Right.
concept of an exponential function.
I know, right?
Well, that is about all the time we have for today's deep dive.
This was fun.
It really was. I learned a lot.
Me too.
To our listeners, thank you for joining us on this mathematical journey.
Yes, thank you.
We hope you found it as illuminating as we did. Until next time, keep those minds curious.